We're happy to have Mert Pilanci with us today. Mert is a professor in electrical engineering in Stanford. I heard today that despite being previously, I think you spent some time in faculty in Michigan, right? But this is the first time in Chicago. So happy that now that he moved to Stanford, he can come visit us in Chicago. And Mert has done a lot of work on optimization, and especially using sketching methods for optimization. And today he's going to be talking to us about how deep networks are actually convex after all. We'll see about that. Okay, thank you.
Thank you so much for the introduction. And thank you so much, Matthew, for hosting me. I will talk about how convex optimization plays an interesting role in non-convex optimization, especially in deep neural network objectives. So we have seen the impact of deep learning for a long time now, and lately ChatGPT became really mainstream. So I asked ChatGPT to explain why neural networks might be useful in statistics. So statistics is a domain where I work a lot on, because convex optimization is really useful and popular in statistical methodologies. And it said, well, certainly neural networks and statistics, they operate in overlapping realms. Well, in statistics, you might have nonlinearity, you might have interacting features which are very complex, so neural networks might be ideal to model it. It also says it's important that neural networks are not always the best tools for the job. They can overfit. They lack interpretability and so on. It's really interesting to me that ChatGPT, which itself is a neural network, actually admits neural networks are not the best tools for the job, which is true, right? And this is really surprising, ChatGPT actually making quite intelligent generations. And then I said, ChatGPT, illustrate this using a diagram, right? Statistical methodology and neural networks, just as an example. Now, it is able to generate images with GPT 4.0, and it has this image. It struggles with the spelling, as usual, but you see this interesting comparison between trusted methods in statistics, like least squares, lasso, logistic regression, which are mostly based on convex optimization, and neural networks, where things are actually a lot less uncertain. We use non-convexity quite a lot. And the things I will show you today are right at this boundary where traditional methods based on convex optimization meet neural networks, deep networks. And it's an interesting boundary. So personally, I work in this intersection, and I'm trying to push this boundary further to the right so that neural networks become more trusted methods. We understand them better. We develop optimization procedures that are more stable, reliable, reproducible. So I have this abstract plot here, number of layers in a deep neural network, where I want you to imagine one layer neural network is essentially a linear model, like a logistic regression model or least squares model, right? And we have seen linear models for autoregressive prediction. This is actually quite old, at least 80-year-old topic. You have least squares-based autoregression models in statistics, right? And now on the other end, we have models which are 500, maybe more layers deep, transformers. We have models like GPT family, BERT, etc., right? So the interesting thing to me is in autoregressive modeling, these models are trained exactly the same way. They minimize the loss, right, of predicting the next item given a history of past values, right? It is exactly the same way linear models are trained. What's different is the model class you're fitting, right, which is a deep neural network. And they have really interesting properties. They generalize on the unseen. For instance, this is what ChatGPT does. When you ask a question, they can translate between different concepts, different languages, say Python to C++ code. They can generate images, objects, videos of things they haven't seen, right? So we observe some quote-unquote intelligence, which is hard to define, but it is actually emerging as we make the models more complicated, although they're trained exactly the same way, using gradient descent, right? So I would like to understand where this complexity comes from. This is a hard question to answer because training is very complex on this end, and we have non-convex optimization. So the general consensus seems you apply gradient descent and it results in some representation. But I feel like that's not the end answer. There should be a deeper mathematical theory that explains this intelligence. At least this is my hope. So there's one traditional way to interpret how a neural network works. So one way is to see each neuron as a correlation detector or matched filter, right? Matched filtering is basically taking a dot product, right? And these dot products are feature extractors. So this kind of a view actually is hitting a bottleneck when you have trillions, millions of neurons. Anthropic published some work on polysemanticity, which means a neuron can be corresponding to more than one concept. When you look at the dot product, for instance, pick a specific neuron in some pre-trained neural network, in this case, this is an inception model, you will see that it will get excited maximally for many different kinds of inputs, and they call this polysemanticity. It looks for more than one meaning, right? Which I think it doesn't make full sense. So I'll offer a different interpretation than this, which will also explain the polysemanticity. So one fundamental challenge, as I mentioned, is non-convexity. This makes it hard to narrow down what model you have at the end of training, because unlike convex optimization, where whatever optimization you use, it will find a global optimum. Here, it is very complicated, but somehow we have this quote-unquote intelligence arising. So lots of challenges remain, like making training inference more efficient, interpreting them, having some foundational theory. So today I will try to argue that convex optimization, and especially sparse models like Lasso, they play an important role in all these aspects, which I find a bit surprising because the problem is non-convex, although I will talk about convex optimization. So here's a high-level overview. I'll first show you that some non-convex problems can be converted to high-dimensional convex optimization. In fact, exactly. And we will analyze these problems, big convex problems, to understand what the neural networks are trying to do. And it will result in a different algebra called geometric algebra, and we will have Lasso models, and we will look at an interpretation of neural network inner operations. So Lasso, I'm sure you have seen the Lasso model, is essentially a linear model fitted with least squares with an added L1 penalty, and this is quite popular in statistics, machine learning, signal processing. The L1 norm encourages sparsity. So many of the coefficients of beta will turn out to be 0, and this is useful to identify what are the most important predictors, the columns of X. And just like Lasso, there is another model which is called group Lasso. So here, the difference is your predictor vector, beta, is partitioned in terms of blocks. And we want most of these blocks to be 0 to identify the relevant groups of predictors. And now you change your regularizer from an L1 norm to sum of L2 norms over these blocks. And this is called group L1 norm regularization. What it will do is, at the solution, most of these blocks will be 0 except a few. And this is also quite popular in statistics and machine learning. So let's dive into one technical result that we have a few years ago. So if you have a 2-layer neural network training objective, immediately, as soon as you have 2 layers, it will be non-convex. So here I have the objective, the loss term, and regularization. The regularization is just sum of squares of all trainable weights. We have 2 trainable weights, W1, W2. The first one is size D by M for D-dimensional features and M neurons. And the second one is M by 1, assuming the output of the network is a scalar, right? And phi is the activation. We will take it to be ReLU, although it can be generalized to other piecewise linear activations. So this problem is non-convex because you have 2 layers and then this nonlinear activation. The regularization here is actually very standard. It's used in even training the biggest models like GPTs. It's called rate decay regularization. And in the linear model world, it is called ridge regularization, or Tikhonov L1, L2 squared penalty. So here's one overview of the first result. Although this problem is non-convex, training the 2-layer neural network to global optimality, there is a convex problem called P-convex. It is using the same laws and a different regularization, R of Z. I will show you what this regularization is very soon. And the variable matrix, the decision variables, are in the matrix Z, which is n by capital P. So this capital P is a larger number, and this problem is essentially an embedding of the first non-convex problem. The second problem is fully convex. In principle, we can solve this. The only issue might be high dimensions, because P is large. But it will turn out that these two problems are identical, equivalent, in the sense that their objective values are the same. And you can transfer the solutions. If you solve the convex problem, you can generate the solution to the non-convex problem, and vice versa. If you have questions, please stop me at any time.
So just trying to get an intuition. So if P is sort of arbitrarily large, is there some reason you don't get a more expressive class than defined by M?
Oh, okay. So I will show you how large P is. The number P is basically dictated by this problem. But
So
they are
P is
sort of the same
P is a function of
complexity.
M. P is a function of M.
Right. So this P is a function of this lambda and the matrix X. I'll show you exactly how that is.
Okay.
How that is connected.
I think, I don't know if this is what, if P is bigger than actually anything, then the question is, you're saying these are equivalent in the sense they can go both ways, right? So it seems there's many more parameters in the second problem than the first problem. So it's maybe a bit surprising that you can go backwards, right? That even though the parameter space is much, much larger,
Right.
you can still go backwards.
True, but to go backwards, all we need to assume, this is an assumption that you need to have enough neurons to do the transfer.
So when you go back and forth, so if I go from the non-convex to convex and back to the non-convex,
Yes.
I'll have it'll be much, the M would be much, much bigger.
I mean, not much, but it should be just enough. I'll show you, right? You just need to have enough neurons to basically plug
But more
them in.
than I started with.
Yes. Yes. If you go this way,
Now if I go back,
or if you go this
if
way,
I go down and then back up, if I go back, then I have an expansion.
well, it might not change actually.
Okay,
In some cases, you might get an expansion.
Okay.
Right. Okay, but to me the interesting thing is once you have a convex objective, then you can study it from the optimization conditions, optimality conditions, right? And then you can develop specialized solvers to it, right? So the complexity, how large this problem is, it's a different issue, which is important. I'll also consider that very soon. Okay, so the theorem says, this is an informal version. I'll show you a more formal version. So the values are identical, and an optimal solution can be obtained to the non-convex problem using the convex problem. And one more important addition, this is actually something we discovered recently. If you look at the optimal set of this problem, it's actually usually not a singleton. It is going to be a set of optimal neural networks. So it turns out that the entire set can be obtained from this convex problem. And the convex problem will have its own optimal set, which is a convex subset. It turns out that they are the same. Basically, it's saying the optimal set of a non-convex problem is actually a convex set. In fact, it will turn out to be a convex polytope. And we can actually compute that, meaning you can compute its vertices.
So when we talk about this optimization program, are you defining this as for fixed P or M, or you like for all M, for all P?
Oh, good question. So we fix the value of M.
And P?
P will be a function of that, function of X, beta and lambda. But we fix M in the first problem, and we need M to satisfy some lower bound. It needs to be greater than some value.
M needs to be like large enough to enumerate all possible sum patterns, which is like n to the power of...
No, not that large, but it has to be larger than some threshold.
Okay.
Okay. Right, so another unexpected thing here is that if you look at local optimal sets, meaning this problem, you have a global optimum. It will also have lots of local optimal points and stationary points. It will turn out that every stationary point is also a convex polytope. And you can find it again from this convex problem. Meaning if you run SGD, for instance, it will converge to a local point, in fact a stationary point, right? Those are also captured by the convex problem. So, okay, here's a slightly more formal version of this theorem and illustrating a specific loss. So here we use the squared loss and we fit our neural network with non-convex optimization. So this is the same problem, but we spell it out, how the objective looks like. It's a sum over little m neurons. The convex problem will take this shape. So the convex problem, in fact, is a group lasso problem with the group lasso penalty, some linear constraints, and in the objective, what we have is same squared loss, but we have some dix, ui minus vi. The optimization variables are ui's and vi's. And di's are fixed. These di's are fixed diagonal matrices. I'll show you what they are. They are basically diagonal zeros and ones. And we do some enumeration over them. And the number p basically comes from how many such distinct patterns are there. And in the theory, you have to assume the number of neurons in your first problem that you set it up, right? It has to be greater or equal than the number of non-zeros to this problem. So you have to have enough neurons for making this conversion possible. But the number of neurons here in the second problem, number of non-zeros, it is controllable by picking the right lambda. And usually when people fit group lasso or lasso models, they fit the entire path of solutions. The path will start from the zero, no non-zeros, and it will scan over the optimal, over lambda to get a path of solutions, right? So this way, actually, by doing the path calculation, you will get a trajectory of neural networks, starting with 0 neurons and then 1 neuron and 2 neurons. So this is actually based on a nice result by Natty and co-authors. So they identified a correspondence in non-convex optimization between this regularization L2 squared and L1. This actually happens because the ReLU function is positive homogeneous, and scaling it will turn this squared regularization to an L1 regularization. This was done in the non-convex optimization first. And this is actually based on, or inspired by that result. This was actually very surprising to me at the time, this result, because here the squared regularization, which doesn't seem like it is going to induce any kind of structure, it actually induces a very important structure. You're going to have a block sparse solution, right? And at some point, in fact, the solution will be entirely zero if lambda is large enough. So I'll show you what the matrices DI, the patterns are.
Are the UI, VI, are they non-negative or?
Oh no, they are not. They are optimization variables, but most of them will turn out to be zero because of this regularization.
Why do you need the UI minus VI? Why? I mean, a bit.
Oh, okay. So why do we need UI minus VI? That's a very good question. So it's actually because the ReLU activation can get a multiplier in the second layer, which is negative. If it's negative, it's switching the sign. So it's accounting for a negative second layer neuron. That's why you have UI minus VI, and you need that. So that's accounting the negative second layer weight.
Wait, what is K, I guess is the question. What is the set K? You didn't tell us.
Oh, okay, I'll show you what this is. These are just linear constraints, but it is not a non-negativity constraint. It's a linear.
Oh, okay, but you do have constraints. But you do have constraints.
Yes.
In them. Okay. Because otherwise, if they're just making sure, if they're unconstrained, then you can just replace the UI. You can merge them, right?
That's
But the constraints
yeah.
is where they're gonna. Okay.
If you had constraints, you could have merged them, and then you can.
Okay. With the linear constraints. Okay, so you're gonna tell us. You still need to tell us what K. Okay.
Yeah.
It's probably what Nacho already said. Or what if you fix UI minus VI? Let's say it be AI, then you certainly can minimize the right second term, and the first one is fixed, so you don't seem to need both UI and VI.
Oh, I think you're suggesting defining a variable
Yes.
in place of UI minus VI.
Yes.
True, we could have done that.
The difference, yeah.
Right, you will get a different problem. But this is the regularization that you have. So over that variable, it's not easy to write out this regularization.
I mean, it's not easy to write down how to minimize the sum of two vectors given the difference.
You have constraints in UNV that you didn't tell us about yet.
Oh, it's K.
Yes,
It's
the-
in K.
Yeah,
Right.
yeah.
Got
On
it,
UI
got
and
it,
VI, there
got
are
it.
some constraints
Got
that
it,
I'll show
got
you
it,
about,
got it,
right?
got it, got
But
it.
these are very simple
Got
constraints.
it.
Okay, so what are those constraints? So I need to tell you what the matrices DI are. So basically, take a look at your samples. Here's an example in 2 dimensions with 3 samples, right? Let's say we have these points, right? We are going to look at linear classifiers and its separation patterns. Okay, so D1 will be the separation pattern of this first linear classifier. The choice of ordering is arbitrary. And this linear classifier classifies all the points towards this side. And the separation pattern is 1, 1, 1. And D1 times X is your data matrix, no change. And there's this classifier, which will give you pattern 1, 1, 0, which is zeroing out the third row. D2X will be this matrix. There's D3, which is all zeros, and D4, 0, 0, 1. And these are only the options if you search over all linear separation patterns. It's a finite list. Then the problem will look exactly like this. This is the convex problem. These are the DI matrices multiplied by X. So basically you get the data matrix, but masked in certain rows, right? And the constraints are linear separation patterns, explaining these linear separations, right? So going back to the previous question, you cannot merge them because of these constraints. But we can interpret what the neural network is doing. This is essentially the same model as a 2-layer ReLU activation neural network. It is a group lasso model. It is fitting a sparse group lasso model. This is your original data matrix, and these are masked versions of it. And it is trying to find the sparsest, in the sense of L1, predictor that fits the data. And it is essentially a piecewise linear model that is trying to be concise, right? If one term fits the model well, it will pick that term, right? And we were interested in this because it's actually applying all the statistical methodology that we know, like L1, group L1, to extract sparse predictors. And it's showing you that ReLU networks, they have the same bias when you fit them with weight decay regularization. So what is the complexity? We should actually talk about this because it has to be exponential time somewhere, right? And this is a nuanced calculation. So if you want to fit a ReLU network architecture with M neurons and N total training samples, and let's say you search over all ReLU patterns on or off, right? So actually you have to check 2 to the mn different possibilities because you have M neurons and on n different samples they take different values, right? This was actually what people considered. But it turns out the convex problem is a lot better because the number of patterns it scales with n over r to power r, where r is the rank of the data. So it is exponential in the rank. And it's possible the rank is small. For instance, your data might be lying in a low rank subspace. But if it is not small, it will be exponential in the dimension, and this cannot be improved unless p is equal to np, even for fitting just one neuron, because it's hard to fit only one neuron. So luckily, in some cases, this is small. R is small. For instance, in radiance field models or convnets, the rank is bounded by the size of your filter. But still, it's a bit problematic. I will offer you a different way to deal with this dimensionality.
Sorry. But
Sure.
what is, so n is the number of data points? So where does d come in? I guess so it's d times, the previous source is d times 2 to the mn, right?
Yes.
And then you have, I'm a bit confused here, but I mean, there's presumably some other, I mean, if the data matrix is actually n-dimensional, if you have lots of data and it's actually, if you have limited data and it's n-dimensional, if you have the dimension is very high, the dimension is very high,
Okay.
and so your data matrix is n-dimensional.
Okay, dimension larger than n or smaller than n?
Dimension is larger than n, and so the n rank n. If your data matrix is rank n, if the points are in general position, if your points are in general position, something seems does the problem indeed become very easy? Because this becomes like 1, right? I mean,
Big O should be taken.
Well, R is, how large is the ranking in that case?
n.
If it's n, this will give you, well, okay.
Big O should be taken inside. It's big O of n divided
Yeah,
by
so it should be big O inside probably, yeah.
Yes, there's big O inside, you're right, yes. This is not going to be 1 if you pick R equals n, yes. True, that's true, yeah. Does that answer your confusion?
I guess so. So
Okay.
really, I should think of it as n to the r, probably.
Yeah, you're right.
Be more
You should
useful.
think of this as n to the r.
Right. Okay.
Okay, so but this number will be large, right? Number of separation patterns, which is roughly the VC dimension of the linear hypothesis class, right? Okay, how do we resolve this issue? Here's one simple idea. But if you have too many variables in a convex optimization problem, you can just subsample the variables, right? How? We can do it randomly. So here's how we do it. We generate random vectors UIs, and then we look at their separation patterns, which is very simple. Generate a bunch of random vectors and then look at their separation patterns and optimize only over these variables with the same objective, right? This is a subsample form of the problem. And in fact, we can use different regularization. It will turn out that if we use p norm here, it corresponds to regularizing p norm squares in the non-convex problem because of the L1, L2 correspondence. So one result here is that if you look at stationary points of the non-convex problem, they are the optimal solution sets for your subsample problem. So essentially it says, if you run SGD and if you hit a stationary point in the non-convex problem, it will actually be in this form. It is going to be a group Lasso problem, only difference being the variables are subsampled. And in fact, all the midpoints of SGD will be in the optimal set of a group Lasso problem. So second, can we get a theoretical guarantee on the optimality gap with a random subsampling of the variables? So this is true if your matrix is sampled from a random Gaussian distribution. So it will turn out that if you pick n over d log n over delta random samples, the subsample convex problem gives you a root log n approximation of the objective. So root log n doesn't seem too small, but you should consider that the objective values, they are actually very small, in fact converging to 0. Because you're fitting a two-layer neural network with enough neurons, it will fit your labels. And if you simulate this, in fact, you see C510 test accuracy with the convex model. As you sample more random planes, it increases. In fact, it can be better than the non-convex SGD optimizer.
Sorry, two questions. Do you need here to make any assumptions about y or y? I mean, how do you choose y after you choose?
On y, there's no assumption.
So
the only assumption is x is randomly sampled.
And then for any y that can be chosen, even based on
Yes.
the entire set x.
Yes, that's true. It's because this result is based on the separation patterns to be evenly distributed. So the hard cases are where the separation patterns are really tiny. There's a low probability separation pattern. But if you have a Gaussian matrix, they are distributed very nicely, uniformly, and a random sample gives you a good approximation.
Okay. And now you're showing us the test accuracy here, which generally is the right thing to show. But I'm actually curious here. The result is actually about empirical optimization. What happens to the empirical objective? I mean,
It's the training objective. It's very small. So, meaning training accuracy will go not to 100%, but close to 90s. And if you optimize it really well, it should go to 100%. So we worked on this direction for a while now, in the past 3 years, and we discovered other model architectures, neural networks, that you can convert to convex programs, meaning the fitting objective becomes a convex optimization problem. So if you have a deep neural network instead of a two-layer neural network, there is a convex problem that we uncovered. The decay pattern will have to be replaced by a product of patterns. And that requires more enumeration, which makes it harder. If you have batch normalization, then the matrices decay X, you need to whiten them. And there's a version that works with batch normalization. Also for transformers, there is a convex problem that we developed. It is going to match exactly, with the difference being the group L1 regularization changes to a group nuclear norm regularization. And this comes from the matrix factorization-like structure in the attention matrix. And here we are using a ReLU attention instead of softmax attention. So not the most usual transformer that you would see. And then for other models like convolutional adversarial networks, and the latest thing we did was diffusion models, we have versions of the convex problem, which will give you the equivalent convex objective for fitting the non-convex model. So the plan for the rest of the talk is, since I showed you the convex equivalence of non-convex problems, now we will dive deeper into just one small problem, and we will increase the depth. And we will look at the convex formulations to understand what is happening as you increase the depth. Okay, because in the first couple slides I told you intelligence emerges as you make the model more complex by adding lots of depth, right? Especially with transformers, right? How does that work out if I am able to convert these problems into convex optimization? And the depth basically gives me more variables. How come more variables translate to more intelligence? So now we will look at a very toy case, which is one-dimensional data. And we are fitting a neural network model of 2 layers. Okay, this is very simple. You are fitting a piecewise linear curve to observe data. And there's very interesting work on this by, again, Nanti and co-authors. They show that if you have an infinitely wide 2-layer ReLU neural network, it can implement a linear spline predictor, which is connect the dots with linear interpolation, and it is actually one of the optimal solutions. So this result shows, since you have group lasso, when you set dimension to 1, group lasso reduces to lasso. And you're going to have this model. In fact, the constraints, they go away. They're always satisfied. This is going to be the optimal solution, and this is for finite neural networks. It's a lasso model in 1D, and the matrix K will have these entries, xi minus xj plus. And I can plot the columns of K. I call them the dictionaries. That's what they use in the lasso literature, because it's fitting the sparse combination of these dictionaries to your target vector y. The dictionaries, they will look like these. These are ramp functions with this special property that the kinks, the breakpoints, are always at training data. And what Lasso does is it identifies the subset of these dictionaries, essentially the subset of training data which support these kinks, the breakpoints, and it fits the label Y. Right, and the optimal prediction that you will get will be a piecewise linear model with breakpoints at a subset of the training data identified by Lasso. So it's a very simple model. Let me illustrate what kind of a fit you're going to get. Let's say you have this toy example, 3 points, 2, 3, 10, with some labels which are not important. This is some arbitrary one-dimensional data set. If you fit this model with this dictionary, right, through Lasso, you're going to get the optimal 2-layer network under weight decay regularization. And it will be something like this with small enough regularization. It's a piecewise linear spline, right, which is very reasonable. This is what a 2-layer neural network does, just linearly interpolate in between the data points. Now, here is the crucial question. Let's say I make my neural network deeper, 3 layers, 4 layers, 5 layers. I will show you equivalent convex problems. What is going to happen to the function you fitted, right? And I was really interested in this because the depth in reality is making your model much more powerful and much more clever. In this one-dimensional example, how can it be more clever? Because this looks like the natural thing to do, right? So keep in mind, all of the models, regardless of the depth, they will be piecewise linear models. But the question is, which piecewise linear model do I fit if I make my model deeper? Okay, so here's the result for 3-layer networks. The convex model is again a lasso, but the distinction is the dictionary matrix, the matrix K, is getting larger as you add depth. In this case, in addition to these ramp-like columns, the dictionaries, you need to add these kind of dictionary elements, which are basically signals with one additional breakpoint. And the most interesting thing is, the additional breakpoints are not at the training data, unlike linear spline interpolation. So here we have a breakpoint at 1, because if you remember, the training data had training points 2, 3, 10. There is a break line introduced as extra breakpoint at 1, and the only reason that's at 1 is 1 is equal distance from 2 as 2 is as far as from 3, meaning it's a reflection of a training point, 3, across another training point. So we have other basis functions like this. So basically reflect every other training point with respect to other training points. If you reflect 2 across 3, you get 4. You can reflect 3 across 10, and you will get 10 plus 7, 17 up here, right? And you include all these features. And then solve Lasso. It will be the optimal 3-layer ReLU neural network. And the function fit can be something like this, with an additional breakpoint here. But note that it is here because 3 and 4 have distance 1 equal to the distance between 2 and 3. So this is actually interesting from my perspective because among all piecewise linear functions, which are getting more and more complicated as you add the depth, this is actually showing you you're going to have a fit that is symmetric in some sense. Here the symmetry is the distance between 2 of your training samples is actually reflected here in your fitted function.
Sorry for asking a bit about details, but I'm trying to. So is this the? So first of all, is for the 1 layer? Are you considering regularized bias or not? And related to that, is this the unique minimizer or? Like
very good question. So this is regularized with weight decay. In the convex formulation, these are L1 regularized.
Okay.
Because of the scaling. Is this the unique optimal solution? That's a very good question. No, in general. But we can get the optimal set. The optimal set will be the optimal set of Lasso.
So but what I'm asking is like, is this solution you showed not an optimal solution for depth 1, and this in the depth 1 optimal solution not an optimal solution for depth 3?
True.
I mean, that's so yeah. So these are not.
Yes.
There's an actual separation.
There's an actual separation, but that depends on your labels too. It's possible that none of these are
No, for that specific
by Lasso.
for that specific example. That you
For
showed.
specific example, yes.
Okay.
Yes. Okay, so this is only for 1D. What happens if it goes higher dimensional, right? So if it's 2-dimensional, then your ReLU activation is kind of like a folded plane, right? And then the analog of this ramp function with a break line at the training data point is a plane that's folded. Like you have this plane and then you fold it. This is a ReLU activation. And what this is doing is essentially, it is giving you the distance to the affine hull of a subset of training data points. So for the 2D version, to fit the convex model, you have to enumerate all these features by getting all pairs of data points and solve Lasso, and that will give you the optimal fit. This is a 2-dimensional version of the ramp. And if you make it deeper, what's going to happen is you're going to have a reflection again, but the reflection is now a reflection of this line, affine hull of a subset of training data samples with respect to another data sample, so that you get a symmetric fold of the function. So if you enumerate this over all subsets of training data, solve it with Lasso, that will give you the optimal 3-layer model. So here I will try to offer an interpretation of this. Why does this happen and what does this mean, right? So I interpret these break lines, which is where the activation line of the ReLU is, as concepts. So this is like the concept generated by 2 of your training samples. And the reflection is translating that concept. It's constructing an analogy, if you will. So let me show you why this makes sense. So imagine natural language processing and specifically language embeddings. Let's say we have the words woman, man, queen, right? So naturally we have another word, king, which is like a reflection of one word here. And we have other words which are reflections of each other, mother and father. Because this axis is like a gender axis, and your concepts are distributed symmetrically with respect to this axis. Another example, let's say you have a program in Python. You would like to transcribe it to C++. This is something transformers do very well. And we have some concepts here. This is a very abstract, toy, cartoonish view of things. We use indentation in Python. In C++, we use curly bracket, right? And the concepts are going to be mirror symmetries of each other, right? So identifying the symmetry axis is actually simplifying the learning task by quite a lot, right? So this is my interpretation of what the reflection created by additional depth is meaning in terms of the concepts you learn. So there's actually a very simple way to illustrate this. So I'll try to show it. So I told you the ReLU activations, they are like folded planes. Right, so they're like folded planes. So inside your neural network, you have a ReLU activation and a linear function. So imagine a linear function representing a one-dimensional subspace, right? So if you have the ReLU activation and this linear function repeated, composed together, right? So what's happening is the ReLU is folding the plane, and the second layer is folding it again. And then your linear function, it pierces through, right? And then you see these reflections. And the deeper it gets, you will see more reflections of reflections, right? And this actually gives you a very interesting symmetry identified by the symmetry axes. So what Lasso does is it actually identifies the symmetry axis in the data that when you fit it, it fits very well. And it is a bit like, instead of learning everything directly, what I'm doing is I'm folding the space and learning the concept so that the symmetries, they are easily learned. And this is actually a very human-like learning ability, because imagine you're learning Python after you learn C++. You don't learn from scratch. What you do is you actually translate, identifying the symmetry axis, and you learn, instead of the curly bracket, I have to use an indentation, right? So I see this as a very human-like learning ability, and this is only enabled by creating folds of folds, which is done by repeated ReLUs. So in the end, you're going to have an extended dictionary, right? And if you fit your convex model with this extended dictionary, you're going to have symmetries, and it will be a better model overall. And this gives a different way to interpret the neurons, as opposed to the dot product interpretation, right? So instead of finding the input that maximize the dot product of the neuron, I think you should be looking at where the break lines of your activations are. Because the function here, in the 1D case, it's this ramp function. It is actually giving you the distance to this training point. But it's directional distance. On the left, it's 0. On the right, it is measuring the distance of this point to this training example. Same in the 2D case. The ramp function is actually the distance function to the affine hull, but it is directional distance. So one thing I realized recently is there's a specific algebra which works really well if you have this directional distance. It's called Clifford's geometric algebra. And it actually simplifies many of these calculations. I'll show you in a couple of slides now. So in Clifford algebra, what you have is a generalization of the complex algebra. It's basically complex algebra in an arbitrary dimension. And all you have to do is, instead of having a vector space, you endow it with additional objects called bivectors, trivectors, k-vectors. These are basically wedge products of lower grade elements. Like if you have two vectors, you form the wedge product. Roughly, it corresponds to an area element. And it is a bivector. And the determinant of this you get here, right? It will give you the area of the parallelogram. It is given by the wedge product, A and B. So this actually simplifies a lot of the algebra related to volumes and complex polygon shapes. So in 2D...
Wait, so how does this generalize to higher dimensions? Like what happens in 3 dimensions?
Right, so I will show you how Lasso generalizes, but the Clifford algebra will have bivectors, trivectors. You will be able to do wedge products of k vectors.
So in k dimensions, I have to take k, the operation is over k vectors. There's no, I can't do an operation over...
You can.
Oh, but then, okay, so you get I see, so for any k, I get the k volume.
Yes,
Okay.
right. So I'll show you specifically the formula. So in 2D, how it works is, in the Lasso formulation, you're going to have k, and the elements of k are described by volumes of triangles. And these triangles, they have a very simple formula with the wedge products. In 1D, it actually simplifies to this formula, which is giving you the ramp function, xi minus xj plus, which in fact is the volume signed volume of the interval xi, xj, and you have the positive part, the ReLU. So in 2D, the generalization is the volume of a triangle, where the sign of the triangle is determined by the directionality of the edges. And in arbitrary dimension, right, the matrix K will have a volume ratio, right? Volume of the parallelotope spanned by these vectors, which is given by a wedge product, right, divided by another wedge product, which is basically a normalized volume of a parallelogram spanned by samples in your data set. And you have to enumerate over all of these and then solve Lasso, right? This Lasso problem is actually very high dimensional.
Wait. But you're taking only the positive part here.
Yes.
How did the positive part disappear from the second thing? In particular, why isn't it infinite many of the times?
So this is,
yeah.
actually, I'm missing a positive part, you're right. So this has to be plus here, yes.
I see. But then it would be half the time this would be infinite.
Okay,
Or a quarter of the time, I guess.
This is only over the non-zero volumes. If you have a zero volume, you don't have this. So yeah, the denominator can be zero, but this is defined only for the non-zero wedge product.
But even if the volume is non-zero, the denominator can still be zero if the volume is negative. The directional volume is negative.
Oh yeah, not including those. So only over the strictly positive wedge products.
Still a bit. The numerator can be positive where the denominator is zero. Is I guess what I'm worried about.
Maybe some probably like last.
So okay, this is calculated only over the indices for which this denominator is
The
non-zero.
denominator is non-zero.
Right.
Yeah. So why?
Yeah.
Is that?
Well, why is that? Because essentially the denominator is a normalization that you get to optimize these columns. So it's essentially a scale factor of the numerator. Right. Yeah, it's a good point you're raising. There are some
that
zero.
seems extremely non-continuous.
Well, it's non-continuous because you have the positive part, right? So the positive part only narrows down a certain orientation of the edges. So the denominator you should only see as a normalization. It's the equivalent of normalizing a vector to unit norm. It is normalizing a wedge product to unit area.
Oh, I see.
If
The
that makes
continuous
sense.
part at the top is also okay. Sorry, I see. I think I see what's going on.
Okay, so if you solve the Lasso problem, what it will do is, remember the regularization that we have. P norm squared corresponds to P norm, and then weight k corresponds to group Lasso. So this will give you the globally optimal neural network, and P is 1. If P is 2, and then it will be epsilon optimal, given that X is a near isometry. And this is true for random Gaussian data. So basically, if you have random Gaussian data, this will give you a near optimal neural network. Otherwise, it will be optimal for P is equal to 1. And the neural network you construct out of this, it will be a piecewise linear function, right? And you can interpret this as the directional distance to affine hulls, which is a different way to interpret ReLU neural networks. And we see these wedge products as concepts. So those concepts look like you take wedge products of subsets of samples, and then they will create this object, which is a volume, right? And Lasso will go over every such combination to fit the labels using these. And reflections, they actually come from the wedge product algebra. So this wedge product will give you, with the absolute value activation, features like this with breakpoints and data points. If you calculate wedge products of wedge products, this is actually giving you, this is actually giving you these reflections. So this is a wedge product of wedge product. And if you get deeper, you will get wedge products of wedge products of wedge products, which is getting iterated with additional breakpoints. And numerically, adding these wedge products of wedge products actually does decrease the test error. This is a simple autoregressive model trained on some Bitcoin trading data. So interestingly, actually, adding reflections of reflections as features will give you better fit. So I'll skip these couple last slides, and I'll jump to the conclusion. So the main takeaway here is deep neural networks, although training problem is non-convex, you can interpret them as very high dimensional convex models. the subsampling process actually gives you a near optimum under some data generation assumptions. And there's a way to express these convex problems using Clifford algebra, which is based on directional distances and wedge products. We have ongoing work on using this theory for fine-tuning and model compression. And there are lots of open problems. One is I would like to build a better foundation for neural network interpretation and training using this kind of a new algebra. And also, these problems are going to be very high dimensional, especially when you have reflections of reflections, tons of optimization variables. Better sampling strategies, identifying the important optimization variables will be really required. So that's all. Thank you so much for your attention. I'd be more than happy to take more questions.
Questions?
So in terms of reflection, does it make a difference if you change the activation from ReLU to absolute value?
Oh, very good question. No, you still get the reflections with absolute value or ReLU. All you have to need is a piecewise linearity with a kink point, right? It might change how many reflections you get, but these are very minor. And one more interesting thing is for other activations, for instance, the linear threshold, the step function, you don't get reflections. Even if your network is very deep, it's only enabled by ReLU or something like ReLU, like leaky ReLU.
But does the regression give you a different solution, different bias? You know?
Well, it does give you different bias because you're changing the dictionary columns, right? It might prefer some other column instead of different columns, yes. It might change the bias, but the bias is always sparsity.
Okay.
So this idea of sort of like reshaping the representation space with these reflections, I'm not sure how to think about that in terms of language models or vision models with a residual stream, right? Where like the representation space seems to be the same throughout the model and then has these like additive pieces bolted onto it throughout. Do you have any thoughts on?
That's a very good question. You're right. So in a transformer, you have a two-layer MLP, but it is a residual connection, right? What does it do to the reflections? Basically, you're adding an identity function, right? I think it does something different, but still there will be reflections. It would be good to investigate. I don't have the full answer, but a very good question.
Yeah, because I like buy this story that you're reshaping the representation space, but it's like unclear what that means when the representation space seems to be like constant.
Yeah.
Also.
I think it will give you newer representations, but I don't know exactly what it does, right? Yeah, good question. I have to think about it.
Going back to the first half of your talk, I'm curious how big does this parameter P have to be both to, so you showed us that you're getting results that are like as good in test performance. I'm curious how large does P have to be to get an actual good approximation for the model itself, like that you have, you can actually go back and find the optimum, and whether you're whether you're getting a significantly different kind of inductive bias here. And,
yeah, good question. I can tell you empirically, if you train and test on CFAR datasets, below 1,000 for the capital M, the number of samples was enough, right? But we also tried on ImageNet. For ImageNet, we needed.
I thought
for CFAR it is.
I thought the x-axis here. Yeah, but the x-axis is P, right?
Yes, it's well, we call it M here. Yes, number of samples.
Okay, but it's number of sampled capital D's, right?
Right. We are sampling out of capital P, capital M random samples, and we are pushing it as high as 256,
right?
Which seems to be enough for CFAR 10.
To actually get
the comparable performance to non-convex optimization.
Comparable performance in terms of test accuracy.
Yes.
Yeah, but in terms of actually approximating the objective, it's not approximating the objective, right? Because otherwise you'd get similar performance.
Yeah.
So how many do you need in order to simulate the objective? And is what's going on here is you're actually getting it seems like you're getting a different inductive bias.
True, you get a different inductive bias. because you have the subsampling going on, true. But it's same kind of inductive bias because we have the same regularization, right? Sum of L2 norms. So in terms of how many we need, I think for C410, it will be a couple thousands. We have done experiments for a couple thousands, and we were getting very similar training loss. But then we tried ImageNet, which has much bigger resolution pictures. For ImageNet, it is a much larger number that we don't know.
Other questions? Yeah, last question.
So you said there's this directional aspect in the wedge product, right? So how does that connect with the reflection? Does it, so you only consider you only allow one direction just to capture the symmetries more efficiently, or
Yeah, that's a good question. The directionality is only because if you have the ReLU activation, it looks like a folded plane, right? And this is directional. This basically activates on this half space. On this half space, this is 0, right? And this is also what's creating the reflection, because when it's folding the space, right, it's creating this reflection. That's why we have it. If you have absolute value activation, for instance, it won't be directional. With absolute value activation, it will be like this, right? It will be already symmetric, like this, and it's not direction; it's just the distance.
Is there a version of this if you go beyond ReLU, like I think two-piecewise polynomial or other?
Yeah. Okay. We tried leaky ReLU, which is a variant of this. We tried polynomial activations that only works up to degree 2. Higher than that will give you hard tensor factorization problems. We tried linear thresholds. So I suspect in practice people are using softer versions of ReLU, like GALU, right? I think it will be similar because you're going to get a soft version of reflection, that's my guess. But this kind of a theory won't work because it's all dependent on the discrete nature of ReLU.
Okay, let's thank Mert again.